Hello everyone, my name is Abdul Halim Hamada and welcome to The Scientific Method, where today we'll be delving deep into the nature and characteristics of light. And by far one of humanity's crowning achievements as a species is being able to take in light and to see it. But light is actually a relic. It is a representation of a time at an instant that the light bounced off of a surface. That means that when I look at you, or I look in the mirror, or even if I gaze up at the stars, I'm actually looking into the past. Because that light that bounced off of you, or that bounced off of my mirror, or the light that came from our very own star, it actually took time to reach my eyes. But the reason to why we can't really tell that there is a time delay, or we can't see the light actually traveling, like a runner sprinting through a track, is because light travels fast, a constant speed of 30 million meters every second. That's fast. That's so fast that light can travel around the Earth not once, not twice, but 8 times in 1 second. So in our daily lives, light speed is so high that it looks like it's just teleporting from one point to another. But what's so interesting and even puzzling scientists ever since we discovered light is that its speed is always the same, 30 million meters every second. When light is traveling, it doesn't lose speed, it doesn't gain speed. From the time that light leaves the surface of a star 1 billion miles away, it will maintain that same speed until it reaches us. Light is a wave, and like all waves, it has a wavelength and a frequency. In fact, there is this equation called the wave equation, obviously named so because scientists are very bad at naming things. Nonetheless though, here it is. The v in the wave equation stands for the speed of the wave. So that's basically how much distance the wave travels in a given time. This weird upside down looking letter y represents the length of the wave, and that's basically the distance between 2 hills or 2 valleys on this wave shown. And f here, which represents the frequency, is how many times that wave is produced. So to get the speed of the wave, you would just multiply these 2 values together. Light is very unique, however, because there's more to light than we can see. Literally. In fact, a whole spectrum of different types of lights representing different behaviors, intensities, and their uses in human society. This here is what we call the electromagnetic spectrum, and it shows us the different types of light you can get just by changing 2 things, either the wavelength or the frequency. It is essentially a cooking book used by humans that shows us the recipes and spices to concoct different types of light, because we use a lot of it. In fact, with a wavelength of 12 centimeters and a frequency of 5 gigahertz, you have radio waves, which gives you access to Wi-Fi, and that is the reason to why you're watching this video. Now, the special thing about light, though, is that it can only travel at one speed, and that's the speed of light, as we discussed earlier. But then looking at the electromagnetic spectrum and then linking it back to the equation, we see that if we change the wavelength or even the frequency, the speed has to change. Well, no, not really, and that's where things get interesting, because all types of light have arranged themselves in a specific manner, and that is, if a certain type of light has a high frequency, then in order for its speed to remain the same, it will decrease its wavelength. So now when you multiply these 2 measurements together, you would get again 30 million meters per second. In fact, going back to the electromagnetic spectrum, as you increase in frequency towards the right, in the same direction, the wavelength decreases. And if you increase in wavelength towards the left, then the frequency decreases in that very same direction, telling us that the speed of light always remains the same, no matter what. And this is dictated by their wavelengths and their frequencies. Now, Galaxies such as our Milky Way and countless of millions of others that exist in the universe actually contain stars. And those stars, just like our sun, emit light. And this light makes its galaxy visible to us. And in fact, we can classify what galaxy we're looking at by this light that's coming at us from all these stars in its galaxy. When the light comes to us from a distant galaxy, though, only certain types of light come, not all of it. Why? Well, because some of the different types of light get absorbed by the stars and the galaxies themselves, and the type of light getting absorbed is the same every time. So on Earth, when we trace out the wavelengths and frequencies that we got from the light, we get the same pattern every time for the same galaxy. We call this pattern its absorption spectrum. So we adapted this as a cosmological tracker of what we are looking at in the universe, because just like the speed of light, this pattern too was constant, different, and specific for each galaxy, like a fingerprint is to a human. But this constancy was short-lived, as in 1915, an American astronomer by the name of Vastus Slipher published a scientific paper stating that he had observed 11 galaxies having different absorption spectrums. What? With all of those galaxies' light shifting down the electromagnetic spectrum, having higher wavelengths of light shifting to the more red part of the visible spectrum. The absorption spectrum changed. This effect to the absorption spectrum was aptly named Redshift. So now arose the question of redshift. What was making the light do this, have a change in their absorption spectrums? And in 1929, lawyer and astronomer Edwin Hubble provided us with the answer. So, there's almost no way that the frequency of light could decrease, so that the wavelength could increase. Well, that is unless you have a giant oscillator just hanging about in the vacuum of space. Very unlikely. But what about changing the wavelength? This doesn't seem too far-fetched. Edwin Hubble took the data of many astronomers at the time, such as Henrietta Leavitt and Vastus Slipher, and he found that the redshift of the galaxies was proportional to the distance of the galaxy from the Earth. Plainly speaking, this meant that the galaxies that were further and further from us were more and more redshifted. This could only mean one thing. The universe was expanding. Wait, but how does this cause redshift? Well, what's actually happening is since our universe is expanding, it's stretching further and further out. The wavelength of light is also stretching further and further because this light is traveling in the universe. This increases the wavelength. And since the speed of light is always constant, due to the wavelength increases, the frequency also decreases in this case. So to make this more understandable, I'm going to use a cosmic short story. This is where I mix abstract storytelling and the logic of science, and I place everything we know in this imaginary world to develop a thought experiment that makes the whole concept more digestible. Imagine that you are in the jaw-dropping metropolis of Toronto, and you are at Rogers Centre Stadium, and you and your friends want to go to the CN Tower. So now the distance to the tower from the Rogers Centre is 400 meters. Not too long a walk, right? But then now, imagine Thanos, a sentient, overpowered being, comes down with the Infinity Gauntlet in his hand, and he uses the Space Stone to increase the size of Toronto by 100 times. Now, this means that the CN Tower, which was just a mere 400 meters away, is now a whopping 40,000 meters away. And this is obviously because the size of Toronto expanded. He did this. So this makes the distances between objects in Toronto 100 times as big. Guys, this is exactly what's happening in the universe. The universe is constantly expanding, so distances between galaxies is always getting larger and larger. The buildings in our cosmic short story represent the different galaxies in our universe, and you, who wants to get from Rogers Stadium to the CN Tower, would be an example of a light wave traveling from one galaxy to another. And that distance that the person is traveling, you, is the wavelength of the light. And the increase of the distance due to the expansion of Toronto is really the universe, which is really the universe expanding in this case, is actually the redshift. Now, as we discussed above, since the wavelength is increasing, for the speed to remain the same, the frequency would also decrease, leaving us with our untampered value of the speed of light. When Edwin Hubble published his findings, there was a shock and uproar in the scientific community, because earlier they had thought that the universe was static. From the beginning of time up till now, the universe had always been the same. That's what they thought. Light, which is the ultimate participator in this discovery, is a slave to the geometry of the universe, and it succumbs to its expansion by changing into its various forms. We humans are blind, and the more that time passes and the more that days go by, the more and more this is further known as the truth. Blind to 6 out of 7 of the light that is available, yet we still claim we can see? But scientists had claimed that the universe is static, but this is the reason to why science and discovery is one of the most humblest experiences known to man. Because scientists make predictions, and just like others, they assume constancy and centralism about our existence, and that our universe is perfect and has always stayed the same. But unlike others, they rejoice at the fact that they are wrong, and they fund expeditions that cure their ignorance.